Picture this. You are floating in the vast emptiness of space, watching as brilliant beams of light streak past you at an incredible speed. These rays of light have traveled millions, sometimes billions of years to reach your eyes. They carry with them the stories of distant stars, ancient galaxies, and cosmic events that happened long before Earth even existed. This light moves at exactly 299,792,458 meters per second. This number represents what we call the speed of light, and for over a century, scientists have believed it to be the ultimate speed limit in our universe. But tonight, we embark on a journey that challenges everything we thought we knew about speed, time, and the very fabric of reality itself. We will explore a fundamental question that has puzzled physicists and dreamers alike. Why can nothing travel faster than light? Is this cosmic speed limit truly absolute? Or could there be hidden pathways through space and time that allow us to break this seemingly unbreakable barrier? Imagine for a moment that you could somehow push an object faster and faster, accelerating it beyond anything we have ever achieved. What would happen if you could make it go faster than light itself? Would time start moving backwards? Would you arrive at your destination before you even left? These questions might sound like science fiction, but they touch on some of the deepest mysteries of our universe. The speed of light is not just a number in a physics textbook. It is woven into the very structure of space and time. It determines how we experience reality, how information travels across the cosmos, and how the universe itself operates. When we look at distant stars, we are not seeing them as they are now, but as they were years or even centuries ago. The light from these stars had to travel across unimaginable distances to reach us, and that journey took time. Yet despite its fundamental importance, the speed of light barrier has always felt like a cosmic joke. Here we are, curious beings with dreams of exploring distant worlds and galaxies, but we seem to be trapped by this universal speed limit. A journey to the nearest star would take thousands of years at our fastest rockets. Even traveling at the speed of light itself, it would still take over 4 years to reach our closest stellar neighbor. But what if this limit is not as absolute as we believe? What if the universe holds secrets that could revolutionize our understanding of speed and travel? Scientists have discovered strange phenomena that seem to bend the rules. Particles that appear to communicate instantly across vast distances. Theoretical constructs called wormholes that could create shortcuts through space itself. Exotic matter that might allow us to warp the fabric of space and time. Tonight, we will explore these possibilities and many more. We will journey through the realm of theoretical physics, where imagination meets rigorous science. We will discover why Einstein believed nothing could travel faster than light, and we will also examine the cutting-edge theories that suggest he might have been wrong. We will meet the mysterious tachyons, particles that exist only in theory, but could travel faster than light from the moment they are created. As we dive deeper into this cosmic mystery, prepare to have your understanding of reality challenged. The universe is far stranger and more wonderful than most of us ever imagine. The speed of light may be the ultimate barrier, or it may simply be the first hurdle in humanity's quest to explore the infinite cosmos. So settle in, close your eyes, and let your mind wander through the vast expanse of space and time as we attempt to answer one of the most profound questions in all of science. Why can nothing go faster than light? And could that actually be possible after all? To understand why nothing can travel faster than light, we must first appreciate just how extraordinary light itself truly is. Light moves at exactly 299,792,458 meters per second in the vacuum of empty space. This might seem like just another number, but it represents something far more profound than a simple measurement. It is a fundamental constant of nature, as unchanging and reliable as the laws that govern the universe itself. When we say light travels at this speed, we are not just talking about the light from your flashlight or the glow from a candle. We are describing the speed of all electromagnetic radiation This includes radio waves that carry your favorite songs across the airwaves, microwaves that heat your food, infrared radiation that you feel as warmth from the sun, visible light that allows you to see the world around you, ultraviolet rays that can give you a sunburn, X-rays that doctors use to see inside your body, and gamma rays from the most energetic events in the cosmos. All of these forms of electromagnetic energy travel at exactly the same speed through empty space. This discovery was not made overnight. For centuries, scientists debated whether light traveled instantaneously or if it had a finite speed. Some of the greatest minds in history grappled with this question. In the 1600s, a Danish astronomer named Ole Rømer made the first successful measurement of light speed by observing the moons of Jupiter. He noticed that the timing of these moon's eclipses seemed to change depending on where Earth was in its orbit around the Sun. When Earth was farther from Jupiter, the eclipses appeared to happen later than expected. Rømer realized this delay was caused by the extra time it took light to travel the additional distance. Over the following centuries, scientists refined their measurements using increasingly sophisticated methods. They bounced light between mirrors, measured the time it took to travel known distances, and eventually arrived at the precise value we know today. But measuring the speed of light was just the beginning. Understanding why this speed is so special would require revolutionary thinking that would forever change our view of the universe. The true significance of light speed began to emerge in the late 1800s, when a Scottish physicist named James Clerk Maxwell developed his equations describing electromagnetic phenomena. These mathematical relationships revealed something startling. The speed of electromagnetic waves, which includes light, appeared to be the same for all observers, regardless of how fast they were moving. This was completely contrary to everyday experience. If you throw a ball from a moving train, the ball's speed relative to the ground is the sum of the train's speed and the speed you threw the ball. But light seemed to behave differently. This strange behavior of light set the stage for one of the most revolutionary ideas in the history of science. A young patent clerk named Albert Einstein pondered this puzzle and arrived at a conclusion that seemed impossible. He proposed that the speed of light in vacuum is the same for all observers, no matter how fast they are moving relative to the light source. This simple statement would become the foundation of his special theory of relativity and would fundamentally change our understanding of space, time, and reality itself. Einstein's insight revealed that light speed is not just fast, it is cosmically significant. It represents the speed at which cause and effect can propagate through the universe. When something happens in one location, the effects of that event can only spread outward at the speed of light. This means that light speed determines how quickly information can travel from one place to another. In a very real sense, the speed of light is the speed of reality itself. Consider what this means for our daily lives. When you look at the moon, you are seeing it as it was about 1 1/3 seconds ago, because that is how long it took the light from the moon to reach your eyes. When you observe the sun, you are seeing it as it was about 8 minutes and 20 seconds in the past. The light from the nearest star beyond our solar system, Proxima Centauri, takes over 4 years to reach us. We see this star not as it is now, but as it was 4 years ago. This cosmic delay becomes even more dramatic when we look at distant galaxies. Some of the light reaching our telescopes began its journey billions of years ago, when the universe was young and very different from what it is today. In effect, astronomy is a form of time travel. We can observe the past by looking deeper into space, because the light from distant objects carries information about conditions that existed long ago. But light speed is more than just a cosmic speed limit for information. It also represents something profound about the structure of space and time themselves. Einstein showed us that space and time are not separate, independent entities as we once believed. Instead, they are woven together into a single fabric called spacetime. The speed of light is the rate at which disturbances can propagate through this fabric. Think of spacetime like the surface of a pond. When you drop a stone into still water, ripples spread outward in all directions at a specific speed determined by the properties of water. Similarly, when events occur in spacetime, the effects spread outward at the speed of light, which is determined by the fundamental properties of spacetime itself. This understanding helps explain why light has maintained its status as the fastest thing in the universe for over a century of scientific investigation. It is not simply that we have not found anything faster. Rather, The speed of light appears to be built into the very architecture of reality. It is the maximum rate at which any cause can produce an effect, the ultimate speed limit for the transmission of information, energy, or influence of any kind. The constancy of light's speed leads us to some remarkable realizations about the nature of our universe. Unlike sound, which travels at different speeds through different materials, light maintains its constant speed through the vacuum of space, regardless of the motion of its source or observer. This consistency is what makes light so special and so fundamental to our understanding of physics. To truly appreciate how extraordinary this is, imagine you are standing on a train platform watching two trains approach from opposite directions. One train is traveling at 50 kilometers per hour toward you, while the other is traveling at 50 kilometers per hour away from you. If someone on each train throws a ball toward you at 20 kilometers per hour relative to their train, the ball from the approaching train will reach you at 70 kilometers per hour, while the ball from the departing train will reach you at only 30 kilometers per hour. This is how we expect velocities to add up in our everyday experience. But light refuses to follow these common sense rules. Whether the light source is moving toward you or away from you, whether you are moving toward or away from the light source, the light always reaches you at exactly the same speed. This bizarre behavior puzzled scientists for decades, until Einstein showed us that our intuitive understanding of space and time was fundamentally flawed. The implications of light's constant speed extend far beyond simple measurements. It tells us that the universe operates according to principles that are often counterintuitive to our everyday experience. When we truly understand what it means for light to have a constant speed, we begin to realize that space and time themselves must be far more flexible than we ever imagined. Consider the journey of a single photon, a particle of light, as it travels from a distant star to your eye. This photon was born in the nuclear furnace at the heart of that star, created when hydrogen atoms fused together to form helium. The tremendous energy released in this fusion process gave birth to our photon, which then began an epic journey that might last thousands or even millions of years. First, the photon had to escape from the dense interior of the star. This alone could take hundreds of thousands of years, as the photon bounced around randomly, colliding with countless other particles in the stellar plasma. Each collision changed the photon's direction, creating a chaotic dance that eventually, through pure chance, led the photon toward the star's surface. Once our photon finally escaped the star's atmosphere, it entered the vast emptiness of interstellar space. Here, traveling at its constant speed of nearly 300 million meters per second, it began its long journey across the cosmos. During this journey, the photon experienced something that would seem impossible to us. From the photon's perspective, if we could somehow adopt its frame of reference, the journey was instantaneous. Due to the strange effects of relativity, time does not pass for objects traveling at the speed of light. This leads us to one of the most mind-bending aspects of light's behavior. While we observe the photon's journey taking years or centuries, from the photon's own perspective, it was created and absorbed in the same instant. This paradox hints at the deeper mysteries we will explore as we delve further into the relationship between light, space, and time. The constancy of light's speed also has profound implications for how we understand energy and matter. Light carries energy, and this energy is directly related to its frequency. Higher frequency light, such as gamma rays, carries much more energy than lower frequency light, such as radio waves. But regardless of their energy content, all forms of electromagnetic radiation travel at exactly the same speed through vacuum. This relationship between light and energy becomes even more significant when we consider Einstein's most famous equation, which relates energy to mass and the speed of light. This equation tells us that mass and energy are interchangeable, and the speed of light serves as the conversion factor between them. In essence, the speed of light determines how much energy is locked up in any given amount of matter. The precision with which we have measured the speed of light is truly remarkable. Modern techniques using lasers and atomic clocks have allowed scientists to determine this fundamental constant to extraordinary accuracy. We now know the speed of light to within a few parts per billion. This precision is not just an academic achievement, it has practical applications in technologies we use every day. Global positioning systems, for example, rely on precise timing signals sent from satellites orbiting Earth. These signals travel at the speed of light, and even tiny errors in our knowledge of this speed would result in positioning errors of many meters. The fact that your smartphone can pinpoint your location to within a few meters is a testament to our precise understanding of how light behaves. The study of light has also revealed other fascinating properties that hint at the deep connections between light and the fundamental structure of reality. Light exhibits what physicists call wave-particle duality. In some experiments, light behaves like a wave, spreading out and interfering with itself to create patterns of brightness and darkness. In other experiments, light behaves like a stream of particles, each carrying a discrete packet of energy. This dual nature of light was one of the key insights that led to the development of quantum mechanics, another revolutionary theory that describes the behavior of matter and energy at the smallest scales. The interplay between relativity, which governs the large-scale structure of space-time, and quantum mechanics, which governs the microscopic world, continues to drive much of modern theoretical physics. As we stand on the shore of our cosmic ocean, gazing out at the vast expanse of space illuminated by countless points of light, we are witnessing the universe's most fundamental messenger in action. Every photon that reaches our eyes carries with it information about distant worlds, ancient events, and the fundamental laws that govern reality itself. The speed of light has become more than just a scientific constant. It represents the cosmic speed limit that shapes our understanding of what is possible and what is forbidden in our universe. It is the thread that weaves together space and time, matter and energy, the past and the future. Understanding why this speed is so special and why it seems to represent an absolute barrier will require us to dive deeper into the revolutionary theories that transformed our understanding of reality itself. Light has long been the reference point for speed, the ultimate measure of how fast anything can travel. But could this boundary be more flexible than we think? In the realm of relativity, the speed of light is not just a limit, it is a cornerstone, a boundary that shapes our entire understanding of the cosmos. But is it a boundary that can never be surpassed? To understand why Einstein's theory of relativity makes the speed of light an absolute barrier, we must first journey back to the early 1900s, when our understanding of space and time was about to be revolutionized forever. Before Einstein, scientists believed that space and time were separate, absolute entities that provided a fixed stage upon which the drama of the universe unfolded. Space was simply empty volume, extending infinitely in all directions, while time flowed uniformly everywhere, like a cosmic metronome keeping perfect rhythm throughout the universe. This view seemed perfectly reasonable. After all, our everyday experience tells us that a minute is a minute whether we are sitting still or moving in a car. A meter is a meter whether we measure it on Earth or imagine measuring it on a distant planet. Space and time appeared to be the unchanging backdrop against which all motion and change occurred. But Einstein dared to question these fundamental assumptions, and in doing so, he discovered that reality is far stranger than anyone had ever imagined. The key insight that led Einstein to his revolutionary theory came from thinking deeply about light and its peculiar behavior. As we discussed earlier, light always travels at the same speed, regardless of the motion of its source or observer. This seemed impossible, according to the classical understanding of motion. If you shine a flashlight while running forward, classical physics would suggest that the light should travel faster in the forward direction, but experiments consistently showed that this was not the case. Einstein realized that if the speed of light is truly constant for all observers, then something else must be changing to compensate. That something else turned out to be space and time themselves. In Einstein's special theory of relativity, space and time are not separate, fixed entities. Instead, they are intimately connected, forming a single four-dimensional fabric called spacetime. This fabric can stretch, compress, and warp in response to motion and energy. The implications of this insight are profound and counterintuitive. According to relativity, when you move through space, you also move through time. The faster you travel through space, the slower you move through time. This effect, known as time dilation, becomes more pronounced as your speed approaches the speed of light. At everyday speeds, the effect is so small as to be unnoticeable, but as you approach light speed, time dilation becomes dramatic. Imagine you are traveling in a spacecraft at 90% of the speed of light. To an observer watching from Earth, your journey to a distant star that is 10 light-years away would take about 11 years. But due to time dilation, you would experience the journey as lasting only about 4.5 years. Your clocks would run slower, your biological processes would slow down, and you would age more slowly than people back on Earth. This is not science fiction or a trick of measurement. Time dilation is a real, measurable effect that has been confirmed in countless experiments. Scientists routinely observe time dilation in particle accelerators, where subatomic particles moving at high speeds live longer than they should according to their normal lifespans. GPS satellites orbiting Earth must have their clocks continuously adjusted to account for time dilation effects, or the system would quickly become inaccurate. But time dilation is just one aspect of how relativity transforms our understanding of high-speed motion. As an object with mass accelerates toward the speed of light, something even more dramatic happens. The object's relativistic mass begins to increase. This does not mean the object gains more atoms or becomes denser in the conventional sense. Rather, its resistance to further acceleration increases, making it harder and harder to speed up. Think of it this way. Imagine you are pushing a shopping cart through a store. At first, the cart accelerates easily with each push. But as you approach the speed of light, it would feel as though the cart is becoming infinitely heavy. Each additional push would produce smaller and smaller increases in speed, even though you are applying the same force. This effect becomes more and more pronounced as you get closer to light speed. Mathematically, Einstein showed that as an object approaches the speed of light, its relativistic mass approaches infinity. This means that infinite energy would be required to accelerate any object with mass to exactly the speed of light. Since infinite energy is impossible to obtain, no massive object can ever reach light speed, let alone exceed it. This energy requirement is not just a theoretical curiosity. We can observe it directly in particle accelerators, like the Large Hadron Collider, where scientists accelerate protons to more than 99.9% of the speed of light. The energy required to achieve these speeds is enormous, and the closer the particles get to light speed, the more energy is needed for each additional increment of speed. It becomes a futile race against the laws of physics themselves. The relationship between energy, mass, and the speed of light is captured in Einstein's famous equation, relating energy to mass. This equation tells us that mass and energy are equivalent, with the speed of light squared serving as the conversion factor. This means that even a tiny amount of mass contains an enormous amount of energy. The speed of light squared is such a large number that converting just 1 kilogram of mass into energy would release the equivalent of about 21 billion kilograms of TNT. This mass-energy equivalence helps explain why the speed of light serves as such a fundamental barrier. As you accelerate an object, you are adding energy to it. According to relativity, this energy manifests as increased mass, which makes further acceleration even more difficult. It is a self-limiting process that becomes impossible to overcome as you approach light speed. The geometric structure of space-time itself also plays a crucial role in establishing the speed of light as a cosmic speed limit. In Einstein's four-dimensional space-time, there is a fundamental distinction between space-like intervals, time-like intervals, and light-like intervals. Objects with mass can only follow time-like paths through space-time, which means they can never reach the boundary defined by light-like paths. To visualize this, imagine space-time as a cone-shaped structure extending into the future. The surface of the cone represents the paths that light rays can take, while the interior of the cone represents all possible paths for massive objects. No matter how much energy you apply to a massive object, its path through space-time must remain inside this light cone. The surface of the cone, where light travels, represents an absolute boundary that massive objects can approach but never reach. This geometric interpretation reveals something profound about the nature of causality in our universe. The speed of light determines the rate at which cause and effect can propagate through space-time. Events can only influence other events if they are connected by a path that light could travel. This ensures that effects never precede their causes, maintaining the logical structure of reality. The universality of this speed limit extends beyond simple mechanical motion. Information, energy, and any form of influence or interaction must respect the light speed barrier. This includes electromagnetic forces, gravitational effects, and even quantum mechanical phenomena. The speed of light represents the maximum rate at which any change or disturbance can propagate through the universe. Einstein's general theory of relativity, which extends special relativity to include gravity, reveals even deeper connections between the speed of light and the fundamental structure of reality. In general relativity, gravity is not a force in the traditional sense, but rather a curvature of spacetime itself. Massive objects warp the fabric of spacetime, and this warping is what we experience as gravitational attraction. Remarkably, gravitational effects also propagate at the speed of light. If the sun were to suddenly disappear, Earth would not immediately fly off into space. Instead, we would continue orbiting for about 8 minutes and 20 seconds, the time it takes for the gravitational change to propagate from the sun's location to Earth at light speed. This delay in gravitational effects was confirmed directly in 2015, when scientists detected gravitational waves, ripples in spacetime itself, traveling at exactly the speed of light. The speed of light also plays a crucial role in determining the structure and evolution of the universe as a whole. Because light has a finite speed, there is a limit to how far we can see into the universe. This boundary, called the cosmic horizon, represents the distance that light has been able to travel since the universe began. Beyond this horizon, there may be more universe, but we can never observe it because light from those regions has not had enough time to reach us. The finite speed of light also means that the universe has a memory. When we look at distant galaxies, we see them as they were billions of years ago. The farther we look, the further back in time we see. This allows astronomers to study the history and evolution of the universe by observing objects at different distances. In effect, the speed of light has preserved a record of cosmic history, frozen in the ancient light that continues to travel toward us across vast expanses of space and time. As we contemplate these profound implications of Einstein's relativity, we begin to understand why the speed of light has maintained its status as the ultimate speed limit for over a century. It is not merely an arbitrary cosmic speed limit imposed by some unknown mechanism. Rather, it emerges naturally from the fundamental structure of spacetime itself. The speed of light is woven into the very fabric of reality, determining how space and time relate to each other, how causality operates, and how energy and matter behave throughout the universe. Yet even as we marvel at the elegance and universality of Einstein's insights, we cannot help but wonder whether this speed limit is truly absolute. Could there be phenomena or mechanisms that transcend even the constraints of relativity? As we continue our exploration of cosmic speed limits, we will discover that while relativity provides powerful arguments for why nothing can exceed the speed of light, the universe may still hold surprises that challenge our understanding of what is possible and what is forbidden. At light speed, everything changes. The very nature of mass and energy shifts in ways that make it impossible to reach, let alone exceed. But what about those things that don't have mass? To truly understand why the speed of light represents an insurmountable barrier for objects with mass, we must delve deeper into the relationship between energy, mass, and motion. This relationship reveals one of the most fundamental truths about our universe, that the laws of physics conspire in a remarkably elegant way to preserve the cosmic speed limit. Imagine you are holding a baseball in your hand. This simple object contains within it an enormous amount of energy, locked away in the bonds between its atoms and in the mass of the particles themselves. When you throw the baseball, you add kinetic energy to it, the energy of motion. In our everyday experience, the faster you throw the ball, the more kinetic energy it has. Double the speed, and you quadruple the kinetic energy. This relationship seems straightforward and predictable. But as we approach the realm of extremely high speeds, something remarkable happens. The simple relationship between speed and kinetic energy that governs our everyday world begins to break down. According to Einstein's theory of relativity, as an object approaches the speed of light, the energy required to accelerate it further grows without bound, approaching infinity as the speed approaches light speed. This is not merely a theoretical curiosity. Scientists observe this effect every day in particle accelerators around the world. When physicists accelerate protons in machines like the Large Hadron Collider, they can achieve speeds of more than 99.9999% of the speed of light. At these incredible speeds, each proton carries thousands of times more energy than its rest mass would suggest. Yet despite pumping enormous amounts of energy into these particles, they never quite reach the speed of light. The mathematics behind this energy increase is both beautiful and inexorable. As an object's speed approaches light speed, the factor by which its energy increases approaches infinity. This means that to accelerate any object with mass to exactly the speed of light would require infinite energy. Since the universe contains only finite amounts of energy, this requirement can never be met. But the story becomes even more fascinating when we consider what happens to the object itself during this acceleration process. According to relativity, the object's relativistic mass increases as it gains speed. This is not the same as gaining more particles or becoming denser in the conventional sense. Rather, the object becomes more resistant to further acceleration, as if it is becoming infinitely heavy. To understand this concept, imagine trying to push a friend on a swing. At first, each push accelerates the swing noticeably. But now imagine that with each push, your friend somehow becomes heavier and heavier. Eventually, even your strongest pushes would barely budge the swing at all. This is analogous to what happens when trying to accelerate massive objects to light speed. The object's resistance to acceleration grows without limit as its speed approaches the cosmic speed limit. This mass increase is not just a mathematical abstraction, it has real, measurable consequences. Particles moving at high speeds in accelerators behave exactly as if they have become more massive. They curve less sharply in magnetic fields, require more force to deflect from their paths, and interact with other particles as if they carry more mass. From every perspective that matters, the particles have indeed become more massive. The energy cost of acceleration reveals itself in another profound way through the relationship between force and acceleration. In everyday life, we expect that applying a constant force to an object will produce a constant acceleration. Push twice as hard, and the object speeds up twice as fast. But as objects approach light speed, this simple relationship breaks down completely. Consider a spacecraft equipped with a perfect rocket engine that can provide constant thrust. At low speeds, this thrust produces steady acceleration, with the spacecraft gaining speed at a constant rate. But as the spacecraft approaches significant fractions of light speed, something strange begins to happen. The same thrust that once produced noticeable acceleration now produces smaller and smaller increases in speed. From the perspective of an observer watching from Earth, the spacecraft appears to be encountering an invisible resistance that grows stronger and stronger as it approaches light speed. Each joule of energy from the rocket engines produces diminishing returns in terms of actual speed increase. The spacecraft's speed approaches light speed asymptotically, getting closer and closer but never quite reaching the ultimate limit. This diminishing return on energy investment is not due to any inefficiency in the rocket engines or any external resistance like friction. It is a fundamental consequence of the structure of spacetime itself. The universe seems designed to prevent massive objects from reaching light speed, no matter how much energy is available or how efficient the propulsion system might be. The mathematical description of this effect reveals a beautiful symmetry in nature. As an object's speed approaches light speed, two things happen simultaneously. The object's relativistic mass approaches infinity, and the energy required to accelerate it further also approaches infinity. These two infinities are perfectly matched, ensuring that the speed of light remains forever out of reach for massive objects. This energy limitation extends beyond simple mechanical acceleration. It applies to any process that could potentially accelerate massive objects to light speed. Whether we consider electromagnetic acceleration, gravitational slingshot maneuvers, or exotic propulsion concepts yet to be invented, the fundamental energy requirements remain the same. The speed of light represents an absolute barrier that cannot be overcome by any amount of cleverness or technological advancement, as long as we are dealing with objects that possess mass. The implications of this energy barrier extend far beyond space travel and particle physics. They touch on some of the deepest questions about the nature of reality itself. Why should the universe be constructed in such a way that infinite energy is required to reach light speed? What is so special about this particular velocity that it represents an absolute boundary? One way to think about this is to consider the speed of light not as a speed limit in the conventional sense, but as a fundamental property of space-time geometry. Just as a circle cannot have corners, or a triangle cannot have four sides, massive objects cannot travel at light speed. The prohibition is not imposed from outside. but emerges naturally from the mathematical structure of reality itself. This geometric interpretation helps explain why the energy requirements become infinite. When we try to accelerate a massive object to light speed, we are essentially trying to make it follow a path through space-time that is geometrically forbidden. The infinite energy requirement is the universe's way of preventing this impossible geometry from being realized. The energy limitations also reveal something profound about the nature of causality and information transfer. Because massive objects cannot reach light speed, and because information cannot travel faster than the objects or fields that carry it, the speed of light automatically becomes the maximum speed for information transfer throughout the universe. This ensures that cause and effect relationships remain logically consistent, with causes always preceding their effects in all reference frames. Interestingly, the energy requirements for approaching light speed also illuminate the deep connection between mass, energy, and the structure of matter itself. When we pump energy into accelerating a particle, we are not just changing its motion, we are fundamentally altering its relationship to space-time. The particle's increased relativistic mass reflects its increased energy content, demonstrating the equivalence of mass and energy that lies at the heart of Einstein's theory. This mass-energy equivalence has profound implications for our understanding of what mass actually is. Rather than being a fixed, unchanging property of matter, mass reveals itself to be a form of concentrated energy. The rest mass of any object represents the energy that would be released if that object were completely converted into other forms of energy. The additional relativistic mass that appears during acceleration represents the kinetic energy that has been added to the object. As we accelerate objects to higher and higher speeds, we are essentially watching the transformation of kinetic energy into what appears to be additional mass. This transformation is perfectly reversible. If we could somehow extract all the kinetic energy from a high-speed particle, its mass would return to its original rest value. The energy we put in during acceleration would be recovered, minus any losses to radiation or other processes. The universality of these energy limitations suggests that they represent something fundamental about the structure of physical law itself. Every known force, and every conceivable acceleration mechanism, runs up against the same infinite energy requirement when trying to accelerate massive objects to light speed. This consistency across all physical phenomena suggests that the light speed barrier is not just an empirical observation, but a fundamental principle that underlies all of physics. Yet even as we marvel at the elegance and universality of these energy constraints, we cannot help but notice an intriguing exception. There exist entities in our universe that do travel at exactly the speed of light. These massless particles seem to dance effortlessly at the cosmic speed limit, unencumbered by the infinite energy requirements that trap massive objects below this threshold. Understanding how massless particles achieve what seems impossible for everything else will be our next step in unraveling the mysteries of cosmic speed limits. Photons, the messengers of light, move without mass. But what if there are other massless particles, or hidden mechanisms, that could travel faster? In the grand theater of the universe, photons play a truly unique role. These fundamental particles of light exist in a realm that seems almost magical compared to our everyday experience with massive objects. While every material thing we know is trapped below the cosmic speed limit by the tyranny of infinite energy requirements, photons dance effortlessly at exactly the speed of light, neither slower nor faster, but precisely at this fundamental boundary of space-time. To understand why photons can achieve what seems impossible for everything else, we must first appreciate what it truly means to be massless. When we say that photons have no mass, we are not simply saying they are very light, like a feather or a grain of sand. We are saying something far more profound. They have no rest mass whatsoever. If you could somehow bring a photon to a complete stop, which is actually impossible, it would have absolutely no mass at all. This massless nature fundamentally changes the rules of the game. Remember how objects with mass require infinite energy to reach light speed because their relativistic mass grows without bound. Photons sidestep this entire problem by having no mass to begin with. There is no mass to increase, no resistance to acceleration, and no infinite energy barrier to overcome. In a sense, photons are born moving at the speed of light and have no choice but to continue at this speed for their entire existence. The life of a photon is unlike anything we can easily imagine. From the moment of its creation until the moment of its absorption, a photon never experiences time as we understand it. Due to the effects of time dilation at light speed, time simply does not pass for a photon. If we could somehow adopt a photon's perspective, its entire journey from creation to absorption would seem instantaneous, regardless of whether that journey takes microseconds or billions of years from our point of view. Consider a photon born in the nuclear fires of a distant star, created when hydrogen nuclei fuse together in the stellar core. From our earthly perspective, this photon might travel for millions of years, crossing the vast emptiness of interstellar space, before finally entering your eye and allowing you to see that distant star. But from the photon's own frame of reference, it was created and absorbed in the same instant. The photon experiences no passage of time during its cosmic journey. This timeless existence of photons reveals something profound about the nature of light-speed travel. At the cosmic speed limit, the normal flow of time that governs our lives simply ceases to exist. Space and time become so distorted that distances shrink to zero and durations become instantaneous. This is not merely a mathematical curiosity, but a fundamental aspect of how the universe operates at its most basic level. Photons also reveal the deep connection between energy and the speed of light. While photons have no rest mass, they do carry energy. The amount of energy a photon carries is directly proportional to its frequency. Higher frequency photons, such as X-rays and gamma rays, carry much more energy than lower frequency photons, such as radio waves and infrared radiation. Yet regardless of their energy content, all photons travel at exactly the same speed through vacuum. This universal speed for all photons, regardless of their energy, tells us something important about the nature of the cosmic speed limit. The speed of light is not dependent on the energy or intensity of the light. A powerful laser beam and a faint starlight both propagate at exactly the same speed. This consistency suggests that the speed of light is determined by the fundamental properties of space-time itself, rather than by the characteristics of whatever is traveling through it. The behavior of photons also illuminates the strange relationship between matter and energy that Einstein revealed in his famous equation. When massive particles are accelerated to high speeds, they gain kinetic energy that manifests as increased relativistic mass. But photons, being massless, cannot gain or lose kinetic energy in the conventional sense. Instead, changes in a photon's energy correspond to changes in its frequency and wavelength, not changes in its speed. This creates a fascinating parallel between massive and massless particles. Just as massive particles cannot reach light speed because doing so would require infinite energy, photons cannot travel at any speed other than light speed. They are locked into this cosmic velocity by their very nature. A photon cannot slow down or speed up, any more than a massive particle can reach light speed. The universe contains other massless particles besides photons. Gluons, which carry the strong nuclear force that holds atomic nuclei together, are also massless and travel at light speed. Gravitons, the hypothetical particles that carry gravitational force, are predicted to be massless as well. Each of these particles, if they exist, would be forever confined to travel at exactly the speed of light, joining photons in their timeless dance at the cosmic speed limit. This raises an intriguing question. Could there be unknown massless particles that travel faster than light? The answer, according to our current understanding of physics, is no. The speed of light is not just the speed that massless particles happen to travel at. It is the maximum speed at which any cause and effect relationship can propagate through space-time. Even hypothetical massless particles must respect this fundamental limit. The reason for this absolute speed limit lies in the geometric structure of space-time itself. Einstein's relativity shows us that space and time are woven together into a four-dimensional fabric. The speed of light represents the fundamental metric of this fabric, determining how distances in space relate to intervals in time. This speed emerges naturally from the mathematical structure of space-time, much like the ratio between a circle's circumference and diameter naturally emerges from the geometry of flat space. In this geometric view, massless particles like photons are not choosing to travel at light speed. They are following the only paths through space-time that are available to them. These paths, called null geodesics by physicists, represent the boundary between the possible and the impossible in space-time geometry. Massive particles must follow paths that curve inside this boundary, while massless particles are constrained to travel exactly along the boundary itself. The study of photons has also revealed the quantum nature of light and energy. Light comes in discrete packets called quanta, with each photon representing the smallest possible amount of electromagnetic energy at a given frequency. This quantization of energy was one of the key insights that led to the development of quantum mechanics, showing that energy, like matter, has a granular structure at the smallest scales. Photons exhibit the strange wave-particle duality that characterizes quantum objects. In some experiments, photons behave like waves, creating interference patterns and diffracting around obstacles. In other experiments, they behave like discrete particles, triggering individual detector clicks and following specific paths. This dual nature suggests that our everyday concepts of particles and waves are inadequate to describe the true nature of reality at the quantum level. The interaction between photons and matter provides another window into the fundamental nature of light-speed travel. When a photon encounters an atom, it can be absorbed if its energy exactly matches the energy difference between two atomic energy levels. The photon disappears completely in this process, transferring all of its energy to the atom instantaneously. There is no gradual transfer or partial absorption. The photon either gives up all of its energy or continues on its journey unchanged. This all-or-nothing interaction between photons and matter reflects the discrete, quantum nature of energy transfer at the microscopic level. It also demonstrates the fundamental role that light speed plays in all electromagnetic interactions. Every force between charged particles, every chemical bond, and every electromagnetic phenomenon ultimately depends on the exchange of photons traveling at light speed. The cosmic microwave background radiation that permeates all of space provides a remarkable example of photons that have been traveling at light speed for over 13 billion years. These ancient photons were released when the universe first became transparent to light, shortly after the Big Bang. They have been racing through the expanding cosmos ever since, carrying with them information about the conditions that existed in the early universe. From the perspective of these ancient photons, their 13 billion-year journey was instantaneous. They were released from the hot, dense plasma of the early universe and immediately absorbed by our radio telescopes, with no subjective time passing between these events. This timeless journey of primordial light provides a direct connection between the present moment and the birth of the cosmos itself. As we contemplate the unique properties of massless particles like photons, we begin to appreciate how the cosmic speed limit creates a fundamental dichotomy in the universe. There are massive particles, which can travel at any speed less than light speed, but can never reach it. And there are massless particles, which must travel at exactly light speed and can travel at no other speed. This creates a sharp boundary in the space of possibilities, with no middle ground between the two regimes. But what if there were particles that somehow transcended this dichotomy? What if there existed entities that were born traveling faster than light, just as photons are born traveling at light speed? Such hypothetical particles would inhabit a realm beyond our current understanding, a faster-than-light universe that would challenge everything we think we know about causality, time, and the structure of reality itself. If light-speed travel is possible, we must ask, what happens when time and space bend? Could breaking this speed limit send us into uncharted territory? To venture beyond the speed of light is to enter a realm where the familiar laws of cause and effect begin to unravel, where the very foundations of logic and reality start to crumble beneath our feet. When we seriously consider what might happen if something could travel faster than light, we discover that we are not just talking about breaking a cosmic speed limit. We are contemplating the destruction of the rational structure that underlies all of existence. Imagine, for a moment, that scientists have somehow built a spacecraft capable of exceeding the speed of light. The crew climbs aboard, waves goodbye to their families, and activates their faster-than-light drive. From the perspective of observers on Earth, something extraordinary and terrifying begins to unfold. As the spacecraft accelerates past light speed, the normal relationship between cause and effect that governs our universe starts to break down in ways that defy all logic and reason. According to the mathematics of relativity, once an object exceeds light speed, its journey through spacetime follows what physicists call a space-like path. This means that the order of events becomes ambiguous and depends on the motion of whoever is observing them. What one observer sees as a cause, followed by an effect, another observer might see as an effect followed by its cause. The spacecraft might arrive at its destination before it departed, creating a logical paradox that threatens the very notion of consistent reality. Consider what this would mean for communication. If you could send a message faster than light, you could potentially receive a reply before you sent the original message. This is not merely a scheduling confusion or a problem with synchronized clocks. It represents a fundamental violation of causality that would make rational thought impossible. You could know the contents of a conversation before having it, receive answers to questions you have not yet asked, and witness effects that precede their causes. The mathematical framework that describes these paradoxes is both elegant and deeply disturbing. Einstein's relativity tells us that simultaneity is relative. Events that appear to happen at the same time for one observer may occur at different times for another observer who is moving relative to the first. This relativity of simultaneity is harmless, as long as no information travels faster than light, but introduce faster than light communication, and the entire logical structure of spacetime collapses into contradiction. To illustrate this breakdown of causality, imagine a thought experiment involving two space stations separated by a great distance. Station A sends a faster than light message to Station B. From the perspective of an observer on Station A, the message travels into the future, arriving at Station B at some later time. But from the perspective of an observer moving at high speed, relative to both stations, the arrival of the message at Station B might occur before it was sent from Station A. Now imagine that Station B immediately sends a faster than light reply back to Station A. From some perspectives, this reply could arrive at Station A before the original message was sent. This creates a causal loop where effects precede their causes, making it impossible to determine what actually happened or in what order events occurred. The universe becomes a place where logic itself breaks down. The most famous illustration of these causal paradoxes is the grandfather paradox, adapted for faster than light travel. Imagine that our faster than light spacecraft not only exceeds the speed of light, but does so in such a way that it travels backwards in time. The crew could theoretically arrive at their destination before they left, meet their younger selves, and potentially prevent their own journey from ever beginning. This creates a logical contradiction that seems to tear at the fabric of reality itself. These paradoxes are not merely philosophical curiosities. They represent genuine mathematical contradictions that emerge whenever we try to incorporate faster than light travel into the framework of relativity. The mathematics that so accurately describes the behavior of the universe at all observed speeds breaks down completely when extended beyond the light speed barrier, suggesting that this barrier represents more than just a practical limitation. The breakdown of causality has profound implications for the nature of free will and determinism. In a universe where effects can precede their causes, the very notion of making decisions becomes meaningless. How can you choose to do something if the consequences of that choice have already occurred? How can you plan for the future if the future can influence the past? The logical foundation upon which all rational thought depends simply dissolves. Some physicists have attempted to resolve these paradoxes by proposing various forms of chronology protection. These hypotheses suggest that the universe has built-in mechanisms that prevent causal violations from occurring, even if faster than light travel were somehow possible. Perhaps the universe would conspire to prevent anyone from actually using faster than light travel to create paradoxes, or perhaps the energy requirements for creating closed time-like curves would always prove to be impossibly large. Another approach to these paradoxes involves the many worlds interpretation of quantum mechanics. In this view, every time a causal paradox would occur, the universe splits into multiple parallel realities, each consistent within itself. Your faster-than-light journey might create an alternate timeline where you prevent your own departure, but this would simply branch off from the original timeline where you did depart. The paradox is resolved by multiplying realities rather than by forbidding faster-than-light travel. However, even these exotic solutions come with their own deeply troubling implications. Chronology protection might require unknown physics that dynamically adjusts the laws of nature to prevent paradoxes. The many-worlds solution implies that faster-than-light travel would constantly create countless new universes, raising questions about the nature of identity and consciousness. that may be even more disturbing than the original paradoxes. The energy requirements for faster-than-light travel present another layer of impossibility. While massless particles travel at light speed and massive particles cannot reach light speed, what would it take to exceed light speed? The mathematical description suggests that faster-than-light travel would require exotic matter with negative energy density, substances that may not exist anywhere in the universe. Even if such exotic matter existed, the engineering challenges would be staggering. Creating a faster-than-light drive might require manipulating the fundamental structure of spacetime itself, harnessing energies comparable to those present during the Big Bang, and controlling forces that we can barely comprehend, let alone master. The technological requirements could be so extreme that they approach the boundaries of what is physically possible, even in principle. The potential existence of tachyons, hypothetical particles that always travel faster than light, adds another dimension to these paradoxes. If tachyons exist, they would inhabit a mirror universe where the faster they travel, the less energy they have. To slow a tachyon down to light speed would require infinite energy, just as accelerating a massive particle to light speed requires infinite energy from our perspective. Tachyons would experience a form of existence that is completely alien to our understanding. They would travel backwards in time from their own perspective, experiencing effects before causes, and living their lives in reverse temporal order. The very concept of tachyonic consciousness or experience becomes paradoxical, as these particles would know their future, but not their past. The detection of tachyons would also create observational paradoxes. A tachyon detector might register the arrival of a tachyon before the event that created it occurred. This could allow us to predict the future with perfect accuracy, at least for events that produce tachyons. The implications for free will and determinism would be profound and disturbing. Perhaps most troubling of all is the possibility that faster-than-light phenomena might already exist in our universe but remain hidden from our direct observation. Some quantum mechanical phenomena, such as the collapse of the wave function, appear to occur instantaneously across arbitrary distances. While this does not involve the transfer of matter or usable information, it does suggest that the universe might contain non-local correlations that transcend the light-speed barrier. The cosmic inflation that occurred during the first moments after the Big Bang involved the expansion of space itself at speeds far exceeding the speed of light. During this period, distant regions of the universe moved apart faster than light could travel between them. However, this did not violate relativity because space itself was expanding. No matter or information actually traveled through space faster than light. These examples hint at the possibility that the light-speed barrier might not be as absolute as it appears. Perhaps there are loopholes in the laws of physics that allow certain types of faster-than-light phenomena while still preserving causality. Or perhaps our understanding of space-time is incomplete, and a more complete theory would reveal new possibilities that we cannot currently imagine. As we contemplate these mind-bending possibilities and paradoxes, we begin to appreciate why the speed of light has maintained its status as an absolute barrier for over a century. Breaking this barrier would not simply allow faster travel and communication. It would fundamentally undermine the logical structure of reality itself, creating a universe where cause and effect become meaningless and rational thought becomes impossible. Yet the human spirit of inquiry cannot help but wonder whether these seemingly insurmountable barriers might one day be overcome. Perhaps there are aspects of reality that we have not yet discovered, hidden mechanisms that could allow faster-than-light phenomena while preserving the consistency of spacetime. The exploration of these possibilities takes us to the very frontiers of theoretical physics, where imagination and rigorous mathematics converge in the search for new understanding. Could tachyons exist in the unseen corners of the universe, offering a glimpse into a realm where light is no longer the limit? In the shadowy realm of theoretical physics, where mathematics meets imagination and possibility dances with impossibility, there exists a class of hypothetical particles, so strange and paradoxical that their very existence would revolutionize our understanding of reality. These are the tachyons, particles that are born traveling faster than light and can never be slowed down to the cosmic speed limit that constrains everything else in our universe. The name tachyon comes from the Greek word tachys, meaning swift or rapid. These particles were first proposed in 1962 by physicist Gerald Feinberg, who wondered whether Einstein's equations might allow for particles that always travel faster than light, just as photons always travel at light speed and massive particles always travel slower than light speed. What Feinberg discovered was mathematically fascinating and physically bewildering. Unlike the massive particles we know, which require infinite energy to reach light speed, tachyons would require infinite energy to slow down to light speed. In the bizarre world of tachyonic physics, the speed of light represents a barrier that tachyons cannot cross from above, just as it represents a barrier that massive particles cannot cross from below. The cosmic speed limit becomes a two-way barrier, with ordinary matter trapped on one side and tachyons forever confined to the other. The mathematical description of tachyons reveals properties so counterintuitive that they challenge our basic understanding of energy, momentum, and causality. As a tachyon moves faster, it actually loses energy rather than gaining it. The fastest moving tachyons would have the least energy, while tachyons with infinite speed would have zero energy. This creates an inverted relationship between speed and energy that is the exact opposite of what we observe with ordinary particles. Imagine a universe where cars use less fuel the faster they go, where rockets become more efficient as they accelerate, and where the ultimate expression of speed requires no energy at all. This is the topsy-turvy world that tachyons would inhabit, a realm where faster movement means less energy rather than more. The implications of such behavior are so strange that they strain the limits of physical intuition. The momentum of tachyons presents an even stranger picture. In our familiar world, momentum and energy both increase together as objects move faster. But tachyons would have imaginary momentum, involving the square root of negative numbers that mathematicians call imaginary numbers. This does not mean that tachyonic momentum is fake or unreal in the everyday sense, but rather that it exists in a mathematical space that extends beyond our ordinary number system. This imaginary momentum creates profound questions about how tachyons would interact with ordinary matter. How do you transfer imaginary momentum to a real object? How do you detect particles whose fundamental properties exist partially in the realm of imaginary numbers? These questions reveal the deep mathematical challenges that tachyons would present to our understanding of physical reality. Perhaps most disturbing of all is how tachyons would experience time. Due to the effects of special relativity, tachyons would experience time flowing backwards relative to ordinary observers. A tachyon would witness events in reverse chronological order, seeing effects before their causes, and experiencing the universe unfolding from future to past rather than past to future. Consider what this backwards time experience would mean for a hypothetical tachyonic consciousness. Such a being would remember the future and be surprised by the past. It would know how conversations end before they begin, witness the outcomes of events before their causes occur, and experience life as a constant journey from known future to unknown past. The very concept of decision-making would become meaningless in such a reverse temporal framework. The interaction between tachyons and the rest of the universe raises fundamental questions about causality and the flow of information. If tachyons could carry information, they would enable communication backwards in time, allowing messages to be sent to the past. This creates the same causal paradoxes we explored earlier, where effects could precede their causes and logical consistency becomes impossible to maintain. Some physicists have proposed that tachyons might exist but be unable to carry usable information, preventing the creation of causal paradoxes. In this view, tachyons might be detectable as statistical correlations or energy fluctuations, but could not be modulated to encode messages. This would allow tachyons to exist without completely destroying the causal structure of spacetime. The search for tachyons has been ongoing for decades, with experiments designed to detect their subtle signatures in cosmic ray showers, particle accelerator collisions, and astronomical observations. Some anomalous results have been reported over the years, including measurements of particles that appeared to travel faster than light. But none of these observations have been confirmed or widely accepted by the scientific community. One of the most famous claims of faster-than-light particle detection occurred in 2011, when researchers at the OPA experiment reported that neutrinos appeared to arrive at their detector slightly earlier than light would have made the same journey. This result, if confirmed, would have provided the first evidence for particles traveling faster than light. However, subsequent investigation revealed that the anomaly was caused by a loose fiber optic cable in the timing system, and the corrected measurements showed that the neutrinos traveled at speeds consistent with but slightly less than, the speed of light. The opera incident illustrates both the excitement and the caution that surrounds the search for faster-than-light phenomena. Such discoveries would be so revolutionary that they require extraordinary evidence and multiple independent confirmations. The burden of proof for tachyonic particles is necessarily very high, given the profound implications such a discovery would have for our understanding of physics. Theoretical work on tachyons has revealed additional puzzles and paradoxes. If tachyons exist and can interact with ordinary matter, they could potentially be used to construct perpetual motion machines or to extract infinite amounts of energy from the vacuum. These possibilities violate well-established principles of thermodynamics and energy conservation, suggesting that tachyons might be forbidden by deeper physical principles that we do not yet fully understand. The quantum mechanical description of tachyons presents its own set of challenges. Quantum field theory, which successfully describes the behavior of all known particles, encounters mathematical difficulties when extended to include tachyonic fields. These difficulties are not merely technical inconveniences, but reflect fundamental problems with the consistency of quantum mechanics in the presence of faster-than-light particles. Some approaches to quantum gravity, the long-sought theory that would unite Einstein's general relativity with quantum mechanics, suggest that tachyons might appear naturally in certain circumstances. String theory, one of the leading candidates for a theory of quantum gravity, predicts the existence of tachyonic modes in some of its mathematical formulations. However, these tachyonic modes are generally viewed as signs of instability rather than as physically meaningful particles. The relationship between tachyons and the structure of spacetime itself raises profound questions about the nature of the cosmic speed limit. If tachyons could exist, they would suggest that the speed of light is not truly fundamental, but rather represents a kind of phase transition in the space of possible velocities. Just as water can exist as ice, liquid, or vapor depending on temperature and pressure, matter might exist in subluminal, luminal, or superluminal phases depending on as yet unknown conditions. This phase transition view of the cosmic speed limit opens up speculative possibilities for technologies that could manipulate the local structure of spacetime to allow transitions between different velocity phases. Perhaps future civilizations could develop methods for converting ordinary matter into tachyonic matter, enabling faster-than-light travel and communication, while avoiding the paradoxes that plague simple faster-than-light motion. The cosmological implications of tachyons are equally fascinating and troubling. If tachyons were produced in the early universe, they might have influenced the formation of large-scale structures like galaxies and galaxy clusters. Tachyonic matter might even comprise some portion of the mysterious dark matter that appears to make up most of the mass in the universe, though its backwards time behavior would make it virtually impossible to detect through conventional means. The philosophical implications of tachyonic existence extend far beyond physics into questions about the nature of time, causality, and free will. In a universe containing tachyons, the future could influence the past, just as readily as the past influences the future. The arrow of time, which gives direction and meaning to our lives, might become bidirectional or lose its significance entirely. Despite decades of theoretical work and experimental searches, tachyons remain purely hypothetical. No confirmed observation of faster-than-light particles has ever been made, and many physicists doubt that such particles can exist in our universe. The mathematical consistency problems, the causal paradoxes, and the lack of experimental evidence all argue against the reality of tachyons. Yet the human imagination continues to be captivated by the possibility of particles that transcend the cosmic speed limit. Tachyons represent the ultimate expression of our desire to break free from the constraints that bind us to subluminal speeds. They embody our dreams of instantaneous communication across vast distances and our fantasies of time travel and causal manipulation. Whether tachyons exist in the hidden corners of our universe or remain forever in the realm of mathematical speculation, they serve an important role in pushing the boundaries of our understanding. By exploring the logical consequences of faster-than-light particles, we gain deeper insights into the fundamental structure of spacetime and the role that causality plays in maintaining the consistency of physical law. As we continue our journey through the mysteries of cosmic speed limits, the enigma of tachyons reminds us that the universe may hold surprises that challenge our deepest assumptions about the nature of reality. Even if tachyons themselves prove to be impossible, the search for ways to transcend the light-speed barrier continues to drive theoretical physics toward new and ever more exotic possibilities. Wormholes could provide a way to traverse the cosmos faster than light, not by speeding up, but by bending space itself. In the vast tapestry of theoretical physics, few concepts capture the imagination quite like wormholes. These hypothetical tunnels through spacetime represent perhaps the most elegant solution to the problem of faster-than-light travel, offering a way to journey between distant regions of the universe without actually exceeding the cosmic speed limit. Instead of breaking the laws of physics, wormholes would exploit the flexibility of spacetime itself, creating shortcuts that could make the impossible journey possible. To understand how wormholes might work, imagine the universe as a vast sheet of paper. Normally, to travel from one point to another on this sheet, you would have to trace a path along the surface, covering every inch of distance between your starting point and destination. But what if you could fold the paper so that your starting point and destination touch? You could then step directly from one point to the other, covering a vast distance in a single step, without traveling along the surface at all. This is essentially what a wormhole would do to spacetime. Instead of forcing travelers to follow the ordinary paths through three-dimensional space, a wormhole would create a tunnel or bridge that connects distant regions directly. The journey through the wormhole itself might cover only a few kilometers, while the equivalent journey through normal space could span thousands of light years. The traveler never exceeds the speed of light during their journey, yet they arrive at their destination far sooner than light could make the trip through ordinary space. The mathematical foundation for wormholes comes directly from Einstein's general theory of relativity. The equations that describe how matter and energy curve spacetime naturally allow for solutions that include these cosmic tunnels. In fact, wormholes were first discovered not in the real universe, but in the mathematical solutions to Einstein's field equations, where they emerged as unexpected consequences of the theory's elegant structure. The simplest type of wormhole, known as an Einstein-Rosen bridge, connects two different regions of spacetime through a throat or tunnel. Picture a funnel with two wide ends, connected by a narrow middle section. Spacetime near each end of the wormhole would curve inward toward the throat, creating a gravitational field that draws matter and energy toward the tunnel entrance. Once inside the throat, travelers would experience a journey through a region of highly curved spacetime before emerging from the other end. However, the Einstein-Rosen bridge presents a fundamental problem that has plagued wormhole physics for decades. According to the original solutions, these wormholes would be highly unstable and would collapse almost immediately after forming. The throat of the wormhole would pinch off so quickly that nothing, not even light, could pass through before the tunnel sealed itself. Any attempt to travel through such a wormhole would result in the traveler being trapped inside a collapsing region of spacetime. To keep a wormhole open and traversable, something extraordinary would be required: exotic matter with negative energy density. This is not simply matter with negative mass, which would be strange enough, but matter whose very existence creates a negative contribution to the total energy of the universe. Such exotic matter would have gravitational properties opposite to ordinary matter, causing spacetime to curve outward rather than inward, and creating the repulsive forces needed to hold the wormhole throat open. The requirement for exotic matter presents enormous challenges for the practical construction of wormholes. Negative energy densities are not completely unknown in physics. They appear in certain quantum mechanical phenomena, such as the Casimir effect, where the quantum vacuum between two metal plates has a lower energy density than empty space far from the plates. However, the amounts of negative energy observed in these quantum effects are incredibly tiny, far too small to support a macroscopic wormhole. Creating the exotic matter needed for a traversable wormhole would require manipulating the quantum structure of spacetime itself on an enormous scale. This might involve creating vast regions where the quantum vacuum has been engineered to have negative energy density, or finding ways to concentrate and amplify the tiny negative energies that already exist in quantum systems. The technological challenges would be staggering, requiring mastery over the fundamental forces of nature at a level that may be impossible to achieve. Even if exotic matter could be created or discovered, the engineering problems would be immense. A wormhole large enough for a spacecraft would need to be supported by exotic matter with a total negative mass energy equivalent to several times the mass of our Sun. This exotic matter would need to be arranged in a precise configuration around the wormhole throat, maintaining perfect stability despite the enormous gravitational stresses involved. The geometry of wormhole spacetime creates additional challenges for travelers. The intense gravitational fields near the wormhole entrance would create extreme tidal forces that could stretch and compress any object attempting to enter. These tidal forces arise because different parts of an extended object experience different gravitational accelerations, with the effect becoming more pronounced as the object approaches the wormhole throat. For a human traveler, these tidal forces could prove lethal unless the wormhole is very large or the exotic matter is arranged to minimize gravitational gradients. A wormhole with a throat only a few meters wide might subject travelers to accelerations millions of times stronger than Earth's gravity, instantly destroying any complex structure. Creating a wormhole safe for human travel would require either enormous size or exotic matter configurations that somehow shield travelers from tidal effects. The temporal aspects of wormhole travel introduce even more complexity. Depending on how the wormhole is constructed and how it moves through space, different ends of the tunnel might experience time at different rates. If one end of a wormhole were accelerated to high speed, while the other end remained stationary, time dilation effects would cause the two ends to age at different rates. This could turn the wormhole into a time machine, allowing travelers to journey not just across space but through time itself. A wormhole time machine would create the same causal paradoxes that plague any form of time travel. Travelers could potentially journey back in time and prevent their own journey from beginning, creating logical contradictions that threaten the consistency of space-time. Some physicists have proposed that the universe has built-in protections against such paradoxes, perhaps through quantum effects, that prevent wormhole time machines from forming or functioning. The study of wormhole physics has revealed connections to some of the most advanced areas of theoretical physics. String theory, which attempts to describe all fundamental forces and particles as vibrations of tiny multidimensional strings, naturally includes wormhole-like structures in its mathematical framework. In string theory, wormholes might connect not just different regions of our universe, but entirely different universes in a vast multidimensional multiverse. Quantum mechanics also plays a crucial role in modern wormhole theory. Some researchers have proposed that quantum entanglement, the mysterious connection that can exist between distant particles, might be related to microscopic wormholes in space-time. In this view, every pair of entangled particles might be connected by a tiny wormhole that allows instantaneous correlation across arbitrary distances. The relationship between wormholes and black holes has been a subject of intense theoretical investigation. Some solutions to Einstein's equations suggest that the interior of a black hole might connect to the interior of a white hole, a hypothetical object that spews matter and energy outward rather than consuming it. The connection between these objects would form a type of wormhole, though one that would be impossible to traverse due to the extreme conditions inside black holes. More recent work has suggested that wormholes might be more common than previously thought, existing as microscopic features of spacetime at the quantum level. These tiny wormholes would constantly appear and disappear in the quantum foam that some theories predict fills all of space. While too small to allow macroscopic travel, these quantum wormholes might play important roles in the fundamental structure of spacetime and the behavior of quantum fields. The possibility of naturally occurring wormholes in our universe remains an open question. Some astronomers have searched for observational signatures that might indicate the presence of wormholes, such as unusual gravitational lensing effects or unexpected patterns in the cosmic microwave background radiation. So far, no convincing evidence for natural wormholes has been found, but the search continues as our observational capabilities improve. The concept of warp drive represents another approach to spacetime manipulation that could enable faster-than-light travel. Unlike wormholes, which create tunnels through spacetime, a warp drive would create a bubble of distorted spacetime around a spacecraft. Inside this bubble, spacetime would be compressed in front of the ship and expanded behind it, allowing the ship to surf on a wave of curved spacetime without actually moving through space at faster-than-light speeds. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, provides a specific mathematical framework for how such a device might work. The spacecraft would remain stationary within its warp bubble, while the bubble itself moves through space at arbitrary speeds. From the perspective of outside observers, the ship would appear to travel faster than light, but from the ship's perspective, it would remain motionless while the universe flows past it. Like traversable wormholes, the Alcubierre drive requires exotic matter with negative energy density to function. The amount of exotic matter needed would be enormous, potentially equivalent to the mass energy of several Jupiter-sized planets. Recent theoretical work has suggested ways to reduce these energy requirements, but they remain far beyond any conceivable technology. The warp drive also faces causality problems similar to those encountered with wormholes. A spacecraft traveling in a warp bubble could potentially arrive at its destination before light signals sent from its starting point, creating the possibility for causal paradoxes. Some physicists have argued that quantum effects would prevent warp drives from achieving truly superluminal speeds, imposing a natural speed limit that preserves causality. Both wormholes and warp drives represent attempts to circumvent the cosmic speed limit through clever manipulation of spacetime geometry, rather than brute force acceleration. These approaches acknowledge the fundamental role of the speed of light, while seeking loopholes that might allow faster than light travel, without directly violating the principles of relativity. The study of these exotic spacetime geometries has pushed theoretical physics into new realms, forcing physicists to confront questions about the nature of energy, the structure of spacetime, and the relationship between geometry and causality. Even if wormholes and warp drives prove impossible to construct, the theoretical investigation of these concepts continues to deepen our understanding of the universe's fundamental laws. As we contemplate these remarkable possibilities for spacetime manipulation, we are reminded that the universe may be far stranger and more malleable than our everyday experience suggests. The rigid spacetime that seems to constrain our movements might actually be a flexible medium that could be shaped and molded by sufficiently advanced technology. Whether such technology is possible in principle, let alone in practice, remains one of the great open questions in theoretical physics. In the quantum realm, particles are not bound by the limits of light. Could quantum entanglement offer a window into faster-than-light communication? Deep within the mysterious realm of quantum mechanics lies a phenomenon so strange and counterintuitive that even Albert Einstein, one of its founding fathers, could never fully accept its implications. This phenomenon is quantum entanglement, a bizarre connection that can exist between particles separated by vast distances, allowing them to influence each other instantaneously across the void of space. Einstein famously dismissed this as spooky action at a distance, but decades of careful experimentation have confirmed that this spookiness is indeed a fundamental feature of our quantum universe. To understand quantum entanglement, we must first appreciate how radically different the quantum world is from our everyday experience. In the classical world that surrounds us, objects have definite properties whether we observe them or not. A coin is either heads or tails, a light switch is either on or off, and a particle has a specific position and velocity at any given moment. But in the quantum realm, particles exist in what physicists call superposition states, where they can be in multiple states simultaneously until the moment they are observed. Imagine a coin that is spinning in the air. While it spins, we might say it is neither definitively heads nor tails, but rather in a superposition of both possibilities. In the quantum world, particles can exist in analogous superposition states, where they are neither definitively here nor there, neither spinning clockwise nor counterclockwise, but somehow both and neither at the same time. This bizarre state of affairs persists until someone makes a measurement, at which point the particle seems to choose one definite state or another. Quantum entanglement occurs when two or more particles become connected in such a way that the quantum state of each particle cannot be described independently. Instead, the particles form a single quantum system, even when separated by enormous distances. When you measure a property of one entangled particle, you instantly know something about the corresponding property of its partner, regardless of how far apart they might be. The classic example involves two particles that are entangled in such a way that their spins are correlated. If one particle is measured to be spinning clockwise, its entangled partner will immediately be found spinning counterclockwise, even if the measurement occurs on the opposite side of the galaxy. This correlation appears to be instantaneous, happening faster than light could travel between the two particles. The creation of entangled particles typically occurs when a single quantum system splits into two parts, or when two particles interact in a specific way. For instance, when certain types of crystals are struck by laser light, they can emit pairs of photons that are entangled in their polarization states. These photon pairs remain connected by the invisible threads of quantum correlation, no matter how far they travel from their source. What makes entanglement so puzzling is that the correlation between entangled particles appears to be stronger than any connection that could be explained by classical physics. In the classical world, if two coins always came up with opposite results when flipped, we would assume that some hidden mechanism determined their outcomes in advance. Perhaps one coin was weighted to favor heads, while the other was weighted to favor tails, or perhaps some other hidden variable controlled their behavior. But quantum entanglement defies such simple explanations. In 1964, physicist John Stuart Bell proved mathematically that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. Bell's theorem showed that if quantum mechanics is correct, then either locality or realism must be false. Either particles can influence each other instantaneously across arbitrary distances, violating locality, or particles do not have definite properties before measurement, violating our common sense notion of realism. Decades of increasingly sophisticated experiments have tested Bell's theorem and consistently confirmed the predictions of quantum mechanics. These experiments have eliminated virtually every conceivable loophole that might allow for classical explanations of entanglement. The evidence is overwhelming that entangled particles do indeed exhibit correlations that cannot be explained by any local hidden variable theory. The implications of these experimental results are profound and deeply unsettling to our classical intuitions. They suggest that the universe is fundamentally non-local, meaning that events in one location can instantly influence events in distant locations without any signal or influence traveling between them. This non-locality appears to operate outside the normal causal structure of spacetime, creating connections that transcend the light-speed barrier. However, it is crucial to understand that quantum entanglement, despite its apparent instantaneous nature, cannot be used to transmit information faster than light. While measuring one particle of an entangled pair instantly affects its partner, this effect cannot be controlled or used to send messages. The outcomes of quantum measurements are fundamentally random, and there is no way to force a particular result that could encode information. To see why information cannot be transmitted through entanglement, consider two scientists, Alice and Bob, who each possess one particle from an entangled pair. When Alice measures her particle, she gets a random result, either spin up or spin down with equal probability. Bob's particle will have the opposite spin, but Bob cannot tell whether his particle's state resulted from Alice's measurement or from some other cause. The correlation is there, but it cannot be detected without classical communication between Alice and Bob to compare their results. This limitation, known as the no communication theorem, ensures that entanglement does not violate the causal structure of relativity. While the quantum correlations themselves appear to be instantaneous, any practical use of these correlations for communication requires classical information transfer, which is limited by the speed of light. In this way, quantum mechanics and relativity maintain their peaceful coexistence, each respecting the fundamental constraints imposed by the other. Nevertheless, the instantaneous nature of quantum correlations has inspired numerous proposals for exploiting entanglement in ways that might circumvent the light-speed barrier. Some researchers have investigated whether entanglement might enable faster-than-light communication through clever protocols that amplify or manipulate the quantum correlations. Others have explored whether entanglement might be related to wormholes or other exotic spacetime geometries that could enable superluminal information transfer. One particularly intriguing possibility is quantum teleportation, a process that uses entanglement to transfer the quantum state of one particle to another distant particle. In quantum teleportation, the original particle is destroyed in the process of measurement, while a distant entangled particle assumes the exact quantum state that the original particle possessed. This creates the appearance that the quantum information has been transported instantaneously across space. However, quantum teleportation still requires classical communication to complete the transfer process. The recipient of the teleported state cannot access the transferred information until they receive classical instructions about how to interpret their quantum measurements. These classical instructions must travel at or below the speed of light, ensuring that quantum teleportation cannot enable faster than light communication, despite its instantaneous quantum correlations. The study of quantum entanglement has also revealed deep connections between quantum mechanics and information theory. Entanglement can be viewed as a form of quantum information that is distributed across multiple particles. This quantum information behaves very differently from classical information, allowing for phenomena like quantum cryptography and quantum computing that have no classical analogues. Quantum cryptography exploits entanglement to create communication channels that are fundamentally secure against eavesdropping. Any attempt to intercept the quantum information inevitably disturbs the delicate entangled states, revealing the presence of an eavesdropper to the legitimate communicators. While this does not enable faster-than-light communication, it does provide a level of security that is impossible to achieve with classical communication methods. Quantum computing represents another revolutionary application of entanglement. Quantum computers use entangled quantum bits, or qubits, to perform certain calculations exponentially faster than classical computers. The massive parallelism enabled by quantum superposition and entanglement allows quantum algorithms to explore vast numbers of possibilities simultaneously, solving problems that would take classical computers longer than the age of the universe. The relationship between entanglement and spacetime geometry has become an active area of research in theoretical physics. Some physicists have proposed that entanglement might be the fundamental building block from which spacetime itself emerges. In this view, the smooth continuum of space and time that we experience might be an emergent property of a deeper quantum network of entangled particles. This entanglement-based view of spacetime suggests that the geometry of space and time might be determined by the pattern of quantum correlations between fundamental constituents of matter and energy. Changes in the entanglement structure could potentially alter the geometry of spacetime, opening up speculative possibilities for manipulating the fabric of reality itself through quantum engineering. The study of entanglement in many particle systems has revealed even more exotic possibilities. In certain quantum materials, entanglement can create collective behaviors that seem to transcend the properties of individual particles. These emergent phenomena include quantum phases of matter with topological properties that make them remarkably robust against external disturbances. Some researchers have speculated that large-scale entanglement in the quantum vacuum might play a role in cosmological phenomena, such as dark energy and cosmic inflation. The quantum vacuum is not truly empty, but filled with fluctuating quantum fields that could be entangled across vast cosmic distances. These entangled fluctuations might influence the large-scale structure and evolution of the universe in ways that we are only beginning to understand. The philosophical implications of quantum entanglement extend far beyond physics into questions about the nature of reality, consciousness, and the relationship between observer and observed. If the universe is fundamentally non-local, connected by invisible threads of quantum correlation, then our classical notions of separateness and independence may be mere illusions created by our limited perspective. Some interpretations of quantum mechanics suggest that entanglement reveals the universe to be a single, indivisible whole, where the apparent separation between objects is a consequence of our classical way of thinking, rather than a fundamental feature of reality. In this view, everything in the universe is connected to everything else through the web of quantum entanglement, creating a cosmic unity that transcends space and time. The practical applications of entanglement continue to expand as our ability to create, manipulate, and detect entangled states improves. Quantum sensors that exploit entanglement can achieve measurement precision that surpasses any classical device. Quantum networks that distribute entanglement between distant locations are beginning to connect quantum computers and communication systems across the globe. As we push the boundaries of what is possible with quantum entanglement, we may discover new phenomena that challenge our current understanding even further. Perhaps there are forms of quantum correlation that we have not yet imagined, or ways of exploiting entanglement that could lead to technologies as revolutionary as quantum computing, but focused on different applications. The mystery of quantum entanglement reminds us that the universe operates according to principles that often defy our classical intuitions. While entanglement may not provide a direct route to faster-than-light communication, It reveals that reality is far stranger and more interconnected than we might have imagined. In the quantum realm, the cosmic speed limit takes on new meaning, not as a barrier to be overcome, but as a boundary that defines the difference between quantum correlation and classical communication, between the possible and the impossible in our interconnected quantum universe. What if the speed of light isn't a fixed rule of the universe, but a temporary illusion? Could we find ways to manipulate it, bending the very fabric of time and space? As we stand at the threshold between known physics and the vast unexplored territories of possibility, we must dare to ask one of the most radical questions in all of science. What if the speed of light, this seemingly immutable constant that has anchored our understanding of reality for over a century, is not actually constant at all? What if this cosmic speed limit is merely an illusion, a temporary artifact of our limited perspective on a universe far stranger and more malleable than we have ever imagined? This question strikes at the very heart of modern physics, challenging assumptions so fundamental that most scientists have never seriously considered alternatives. Yet as our understanding of the universe deepens and our experiments probe ever more exotic realms of space and time, hints are emerging that the speed of light might not be the unchanging bedrock of reality that we have long believed it to be. The first clues that the speed of light might be variable come from cosmology, the study of the universe as a whole. When astronomers look deep into space, they are also looking back in time, observing the universe as it existed billions of years ago. Some of these observations suggest that the fundamental constants of nature, including the speed of light, might have been different in the early universe than they are today. The evidence comes from studying the light emitted by distant quasars, incredibly bright objects powered by supermassive black holes in the hearts of ancient galaxies. When this light passes through clouds of gas between the quasars and Earth, it creates absorption lines that act like cosmic fingerprints, revealing the properties of atoms billions of years ago. By carefully analyzing these absorption lines, some astronomers have found subtle differences that could indicate changes in fundamental constants over cosmic time. If the speed of light has indeed changed since the universe was young, this would revolutionize our understanding of physics and cosmology. It would suggest that what we consider to be fundamental constants are actually variables that evolve along with the universe itself. The implications would be staggering, affecting everything from our understanding of stellar evolution to the nature of space and time. The possibility of a variable speed of light also emerges from theoretical work on quantum gravity, the long-sought theory that would unify Einstein's general relativity with quantum mechanics. Some approaches to quantum gravity suggest that space and time themselves might have a granular structure at the smallest scales, composed of discrete units rather than forming a smooth continuum. In such a universe, the speed of light might depend on the detailed structure of this quantum spacetime foam. If spacetime has a granular structure, then light might experience something analogous to dispersion, the phenomenon that causes different colors of light to travel at slightly different speeds through certain materials. Just as white light separates into a rainbow when passing through a prism, light of different frequencies might travel at slightly different speeds through quantum spacetime, with the differences becoming noticeable only over cosmic distances or at extreme energies. This quantum spacetime dispersion could manifest in several ways. High-energy photons, such as gamma rays, might travel slightly faster or slower than low-energy photons, such as radio waves. The differences would be incredibly tiny, perhaps detectable only in light that has traveled billions of light-years from distant astronomical sources. But if such differences exist, they would indicate that the speed of light is not truly universal, but depends on the energy of the light itself. Several astronomical observations have searched for evidence of such dispersion effects. When distant gamma-ray bursts, the most powerful explosions in the universe, release bursts of high-energy photons. These photons race across the cosmos toward Earth. If quantum spacetime dispersion exists, the highest energy photons should arrive at Earth slightly before or after the lower energy photons, depending on the detailed structure of spacetime. So far, these searches have found no convincing evidence for quantum spacetime dispersion, placing strict limits on how granular spacetime can be. But the absence of evidence is not evidence of absence, and future observations with more sensitive instruments might yet reveal the subtle signatures of quantum spacetime effects. Another approach to varying light speed comes from theories that propose additional dimensions beyond the 3 spatial dimensions and 1 time dimension that we directly experience. In these extra-dimensional theories, our familiar universe might be a thin slice or membrane floating in a higher dimensional space. The speed of light that we measure might depend on how light propagates through these extra dimensions, potentially varying from place to place or time to time. Some extra-dimensional theories suggest that gravity might leak into these additional dimensions, becoming stronger at very short distances than Einstein's theory predicts. If light also interacts with these extra dimensions, its speed might vary depending on the local gravitational environment or the detailed geometry of the extra-dimensional space. This could create regions where light travels faster or slower than its familiar speed in vacuum. The concept of metamaterials has opened up entirely new possibilities for manipulating the speed of light on smaller scales. Metamaterials are artificially structured materials with properties that do not occur naturally, designed to interact with electromagnetic radiation in exotic ways. Some metamaterials can slow light down dramatically, reducing its speed to a crawl or even bringing it to a complete stop. Others can make light appear to travel faster than its speed in vacuum. While these metamaterial effects occur only within the structured material itself and do not represent true faster-than-light travel, they demonstrate that the effective speed of light can be dramatically altered through clever engineering. This raises the speculative possibility that sufficiently advanced technology might be able to modify the properties of spacetime itself, creating regions where light naturally travels at different speeds. The study of Bose-Einstein condensates, ultra-cold clouds of atoms that behave as a single quantum entity, has revealed even more exotic possibilities for light manipulation. In these quantum systems, light can be slowed to speeds of meters per second, or even brought to a complete stop, with the optical information stored in the atomic medium. When the light is later released, it continues on its journey as if nothing had happened. These experiments with slow light and stopped light hint at the possibility that the speed of light might be far more malleable than we have traditionally assumed. If the quantum properties of matter can so dramatically alter light's behavior, perhaps the quantum properties of spacetime itself could be engineered to achieve similar effects on a cosmic scale. The relationship between the speed of light and other fundamental constants provides another avenue for exploring variability. The speed of light is intimately connected to the electric permittivity and magnetic permeability of free space, 2 quantities that determine how electric and magnetic fields behave in vacuum. If these properties of space itself could be altered, the speed of light would change accordingly. Some theories suggest that the vacuum of space is not truly empty, but filled with quantum fields that constantly fluctuate between existence and non-existence. These quantum vacuum fluctuations might be responsible for determining the fundamental constants of nature, including the speed of light. If the properties of the quantum vacuum could be modified through some unknown mechanism, the fundamental constants might change as well. The concept of vacuum engineering, manipulating the quantum properties of empty space, represents one of the most speculative frontiers in theoretical physics. If we could somehow alter the quantum vacuum, we might be able to create regions where the speed of light is different from its normal value. Such technology would represent the ultimate form of space-time engineering, giving us control over the most basic properties of reality itself. The study of cosmic inflation, the period of exponential expansion that occurred in the first moments after the Big Bang, provides hints that spacetime itself might be far more flexible than our everyday experience suggests. During inflation, space expanded faster than light, carrying distant regions of the universe beyond each other's horizons. This faster-than-light expansion did not violate relativity because it involved the expansion of space itself rather than motion through space. The fact that space can expand faster than light suggests that the geometry of spacetime is not rigidly fixed, but can be dynamically altered under extreme conditions. If inflation could cause space to expand at superluminal speeds, perhaps other mechanisms could cause local regions of space to contract, effectively increasing the speed at which signals can travel between distant points. Some speculative theories propose that dark energy, the mysterious force driving the current acceleration of cosmic expansion, might be related to the properties of the quantum vacuum. If dark energy can alter the expansion rate of the universe, it might also be capable of modifying other properties of spacetime, potentially including the speed of light itself. The possibility that fundamental constants might vary has led to the development of alternative theories of gravity and cosmology. Some of these theories, such as varying speed of light cosmology, explicitly incorporate changes in the speed of light as a fundamental feature. In these theories, the evolution of the universe is driven not just by matter and energy, but also by the changing values of fundamental constants. Varying speed of light cosmology offers alternative explanations for some of the puzzling features of our universe. For example, the remarkable uniformity of the cosmic microwave background radiation across the sky suggests that distant regions of the universe were once in causal contact, even though they are now separated by distances that light could not have traveled since the Big Bang. Varying speed of light theories propose that light traveled much faster in the early universe, allowing these distant regions to communicate and reach thermal equilibrium. The search for evidence of varying fundamental constants has become an active area of experimental and observational research. Atomic clocks, the most precise timekeeping devices ever created, are used to search for tiny changes in the fundamental constants over human timescales. So far, these experiments have found no evidence for variability, but they continue to improve in precision and may eventually detect changes too small to observe with current technology. Laboratory experiments with exotic matter and extreme electromagnetic fields are also searching for situations where the speed of light might deviate from its standard value. Some theories predict that intense electric or magnetic fields could alter the properties of the quantum vacuum, potentially affecting the speed of light in ways that might be detectable in carefully controlled experiments. The philosophical implications of a variable speed of light are profound and far-reaching. If the speed of light is not truly constant, then many of our most basic assumptions about the nature of reality might need to be reconsidered. The concepts of simultaneity, causality, and the arrow of time are all intimately connected to the constancy of light speed. Changes in this fundamental parameter could affect our understanding of free will, determinism, and the relationship between past, present, and future. The possibility that we might someday learn to manipulate the speed of light opens up speculative scenarios that seem more like science fiction than science fact. Imagine regions of space where light travels at different speeds, creating optical illusions on a cosmic scale. Picture spacecraft that surf waves of modified space-time, riding currents of altered light speed to traverse the galaxy in record time. Even more exotic possibilities emerge when we consider the relationship between the speed of light and the structure of causality itself. If the speed of light could be increased in certain regions, the light cone structure that determines which events can influence each other would be expanded, potentially allowing new forms of causal connection across space and time. As our exploration of the speed of light reaches its conclusion, we are left with more questions than answers. The speed of light remains one of the most precisely measured quantities in all of physics, yet our understanding of why it has the value it does, and whether that value is truly fundamental, continues to evolve. The universe may yet surprise us with revelations that challenge our most basic assumptions about space, time, and the nature of reality itself. Whether the speed of light proves to be an absolute constant or a variable parameter that can be manipulated and controlled, our journey through the mysteries of cosmic speed limits has revealed the incredible richness and complexity of the universe we inhabit. From the elegant mathematics of relativity to the bizarre phenomena of quantum mechanics, from the exotic possibilities of wormholes to the mysterious connections of entanglement, we have seen that reality is far stranger and more wonderful than our everyday experience might suggest. Though the speed of light remains an unbroken limit, the universe is vast, and our understanding of space and time continues to evolve. What we once thought impossible may one day become a reality. As we stand at the threshold of a new era in space exploration, our journey through the mysteries of cosmic speed limits brings us to contemplate humanity's future among the stars. While the speed of light continues to stand as an apparently insurmountable barrier, our ever-deepening understanding of physics, coupled with revolutionary advances in technology, may yet reveal pathways to the cosmos that we can barely imagine today. The next century of space exploration will likely witness transformations as profound as those that carried humanity from the first powered flight to landing on the moon in less than 70 years. Just as the Wright brothers could never have envisioned spacecraft capable of traveling to Mars or robotic probes exploring the outer reaches of our solar system, we may be equally unable to foresee the technologies that will define space travel in the 22nd century. Current propulsion technologies, while remarkably advanced compared to the chemical rockets that first carried humans into space, still operate far below the cosmic speed limit. Ion drives, which accelerate spacecraft using electric fields, can achieve much higher speeds than chemical rockets, but still require years or decades to reach the outer planets. Solar sails, which harness the pressure of sunlight for propulsion, offer the promise of continuous acceleration, but produce only tiny forces that accumulate slowly over vast distances. The development of fusion propulsion represents one of the most promising near-term advances in space exploration technology. Fusion rockets would harness the same nuclear processes that power the stars, converting small amounts of matter directly into energy with incredible efficiency. Such engines could potentially accelerate spacecraft to significant fractions of light speed, perhaps 10 to 20% of the cosmic speed limit, making interstellar journeys possible within human lifetimes. The challenges of fusion propulsion are immense, requiring mastery over nuclear processes that we are only beginning to understand on Earth. Creating controlled fusion reactions in the weightless environment of space, managing the intense radiation and heat produced by the fusion process, and designing spacecraft capable of withstanding the enormous stresses of high-speed travel, all present technological hurdles that may take generations to overcome. Even more ambitious propulsion concepts push the boundaries of known physics while remaining theoretically possible within the framework of established science. Antimatter propulsion, which would annihilate matter and antimatter to produce pure energy, could achieve the highest possible efficiency for any propulsion system. A spacecraft powered by antimatter could potentially reach speeds approaching significant fractions of light speed, though the technological challenges of producing, storing, and handling antimatter safely remain staggering. The production of antimatter requires enormous amounts of energy, with current techniques producing only microscopic quantities at costs that exceed the gross domestic product of entire nations. Storing antimatter presents additional challenges, as any contact with ordinary matter results in immediate annihilation. Advanced magnetic containment systems would be needed to hold antimatter fuel safely away from the spacecraft structure, requiring technologies that may not be feasible for centuries to come. Breakthrough Starshot, an ambitious research program led by physicist Stephen Hawking and internet entrepreneur Yuri Milner, represents one of the most concrete attempts to develop interstellar travel technology using known physics. The project proposes using powerful laser arrays to accelerate tiny spacecraft, each no larger than a computer chip, to 20% of light speed. These miniature probes could reach the nearest star system in about 20 years, transmitting data back to Earth about potentially habitable planets. The technical challenges facing Breakthrough Starshot illustrate both the promise and the difficulty of high-speed space travel. The laser system would need to deliver precisely controlled beams with power levels comparable to those used by entire cities, focusing this energy on spacecraft smaller than postage stamps traveling at relativistic speeds. The miniature probes would need to survive the intense acceleration, navigate through interstellar space, and communicate across light years using transmitters smaller than cell phone antennas. While such projects push the boundaries of current technology, they remain grounded in well-understood physics. The real breakthroughs in space exploration may come from discoveries that fundamentally alter our understanding of space, time, and the nature of reality itself. Advances in quantum mechanics, our growing understanding of dark matter and dark energy, and potential discoveries about the structure of spacetime could open entirely new possibilities for cosmic travel. Quantum computing represents one area where revolutionary advances might impact space exploration in unexpected ways. Quantum computers could potentially solve complex navigation and optimization problems that are impossible for classical computers, enabling spacecraft to plot optimal courses through the gravitational fields of multiple bodies, or to coordinate the activities of vast swarms of robotic explorers. Quantum sensors might detect gravitational waves or other subtle space-time distortions, revealing new information about the structure of the universe. The development of artificial intelligence and machine learning could also transform space exploration by enabling spacecraft to operate independently across the vast distances and time delays that characterize interstellar travel. Advanced AI systems could adapt to unexpected situations, make complex decisions without human input, and even evolve new capabilities during long-duration missions. Such autonomous spacecraft might explore star systems for decades or centuries, continuously learning and adapting as they encounter new environments. The search for exotic matter and new physical phenomena continues to drive theoretical research that could eventually lead to revolutionary propulsion technologies. Scientists are investigating the properties of dark matter, which appears to make up most of the matter in the universe, but interacts with ordinary matter only through gravity. If dark matter could be harnessed or manipulated, it might provide new mechanisms for spacecraft propulsion that we cannot currently imagine. The study of quantum vacuum fluctuations has revealed that empty space is not truly empty, but filled with constantly appearing and disappearing virtual particles. Some theories suggest that these vacuum fluctuations might be exploited to extract energy or create propulsive forces, though such possibilities remain highly speculative. The Casimir effect, which creates attractive forces between closely spaced metal plates due to quantum vacuum effects, demonstrates that the quantum vacuum can produce measurable forces, though scaling such effects to useful levels for spacecraft propulsion presents enormous challenges. Advances in materials science continue to push the boundaries of what is possible for high-speed spacecraft. Carbon nanotubes, graphene, and other advanced materials offer strength-to-weight ratios that far exceed anything available to earlier generations of engineers. Metamaterials with carefully designed structures could potentially manipulate electromagnetic radiation in ways that enable new forms of propulsion or protection from the hazards of high-speed travel. The development of self-replicating robotic systems could revolutionize space exploration by enabling the construction of massive infrastructure projects in space. Self-replicating probes could travel to nearby star systems and use local materials to build copies of themselves, creating an exponentially expanding network of explorers that could survey the entire galaxy within a few million years. Such systems could also construct large-scale engineering projects, such as Dyson spheres around stars or massive particle accelerators in space. The prospect of uploading human consciousness into digital form represents one of the most speculative but potentially transformative developments for space exploration. If human minds could be digitized and transmitted as information, interstellar travel could become as simple as sending radio signals across space. Digital consciousnesses could travel at light speed between star systems, experiencing subjective time at whatever rate they choose, while their information patterns cross the cosmic void. While consciousness uploading remains purely speculative, advances in neuroscience and computer technology continue to deepen our understanding of how the brain processes information and creates subjective experience. Brain-computer interfaces are already allowing paralyzed patients to control external devices with their thoughts, suggesting that the boundary between biological and artificial intelligence may become increasingly blurred in the coming decades. The discovery of life beyond Earth could profoundly impact the future of space exploration by providing new motivations for interstellar travel and new models for how life might adapt to extreme environments. If life is found to be common throughout the galaxy, the search for habitable worlds and the potential for contact with other civilizations could drive technological development in ways that we cannot currently predict. The potential for genetic engineering and synthetic biology to create organisms specifically adapted for life in space opens up new possibilities for biological space exploration. Genetically modified organisms could potentially survive and thrive in the vacuum of space, on the surfaces of other worlds, or in the interstellar medium itself. Such organisms could serve as living spacecraft, carrying out exploration missions while reproducing and evolving in alien environments. The development of closed-loop life support systems represents a crucial step toward enabling long-duration space missions. Advanced recycling technologies that can convert waste products back into food, water, and breathable air with near-perfect efficiency would free spacecraft from dependence on supplies from Earth. Such systems could enable multi-generational voyages to nearby star systems, allowing human crews to survive journeys lasting centuries or millennia. Space-based manufacturing could enable the construction of spacecraft and space habitats on scales that would be impossible to launch from Earth's surface. Asteroid mining could provide virtually unlimited raw materials for space construction projects, while solar power satellites could supply the enormous amounts of energy needed for advanced propulsion systems. The development of space-based industry could transform space exploration from a limited scientific endeavor into a major economic activity that drives rapid technological advancement. The concept of generation ships, massive spacecraft designed to support human populations for centuries or millennia, represents one approach to interstellar colonization that does not require faster-than-light travel. These enormous vessels would essentially be mobile worlds, complete with ecosystems, cities, and all the infrastructure needed to support human civilization. The passengers would live their entire lives aboard the ship, with multiple generations passing before the vessel reaches its destination. The psychological and social challenges of generation ship voyages would be immense, requiring new forms of governance, education, and cultural preservation that could maintain social cohesion across centuries of travel. The inhabitants would need to maintain the motivation and technical knowledge necessary to complete their mission, despite never seeing their destination themselves. Such voyages would represent the ultimate test of human commitment to space exploration and the expansion of consciousness throughout the cosmos. The search for breakthrough physics continues to drive research into phenomena that could revolutionize our understanding of space and time. The discovery of new fundamental particles, forces, or dimensions could reveal possibilities for faster-than-light travel that we cannot currently imagine. Advances in string theory, loop quantum gravity, and other approaches to quantum gravity might uncover new aspects of space-time geometry that could be exploited for propulsion. The development of technologies for manipulating space-time itself represents the ultimate goal of advanced propulsion research. If the fabric of space and time can be engineered and controlled, then the apparent impossibility of faster-than-light travel might prove to be merely a limitation of our current understanding rather than a fundamental barrier. The creation of wormholes, warp drives, or other exotic space-time geometries could transform interstellar travel from a centuries-long odyssey into a routine journey. As we contemplate these extraordinary possibilities for the future of space exploration, we must remember that the greatest discoveries often come from unexpected directions. The quantum mechanics that underlies much of modern technology emerged from investigations into the behavior of heated objects. The general relativity that provides our best understanding of gravity and spacetime arose from attempts to reconcile electromagnetism with special relativity. The technologies that will carry humanity to the stars may similarly emerge from basic research into phenomena that seem completely unrelated to space travel. The human drive to explore and understand the universe appears to be a fundamental aspect of our nature, pushing us always toward new frontiers despite the enormous challenges involved. As we continue to probe the mysteries of cosmic speed limits and the nature of space-time itself, we may discover that the universe holds surprises that make even our most ambitious dreams of interstellar travel seem modest in comparison. The cosmos awaits, vast and full of wonders, ready to reveal its secrets to those bold enough to seek them out. The universe is full of mysteries, many of which we have yet to uncover. As we continue to explore the cosmos, we will push the boundaries of what we thought possible. And in that search, we may one day find that the speed of light was just the beginning of a much larger journey. As our journey through the mysteries of cosmic speed limits draws to a close, we find ourselves standing at the edge of the known universe, gazing out into an infinite expanse of possibility and wonder. We have traveled together through the elegant mathematics of relativity, witnessed the strange dance of quantum particles, and contemplated technologies so advanced they seem indistinguishable from magic. Yet for all we have discovered, for all the boundaries we have explored, we remain humbled by the vastness of what we do not yet know. The speed of light, that seemingly absolute barrier that has shaped our understanding of reality for over a century, may indeed represent a fundamental limit written into the very fabric of space-time. Or it may prove to be merely the first of many cosmic boundaries waiting to be understood, challenged, and perhaps transcended. The universe has surprised us before with revelations that seemed impossible until the moment they were discovered to be true. Think back to the scientists of previous centuries who believed that heavier-than-air flight was impossible, that the atom was indivisible, or that space and time were absolute and unchanging. Each of these seemingly obvious truths was overturned by careful observation, bold thinking, and the relentless human drive to understand the world around us. The speed of light barrier, formidable as it appears, may one day join this list of conquered impossibilities. Our exploration has revealed that the universe operates on principles far stranger than our everyday experience suggests. Particles can exist in multiple states simultaneously until observed. Empty space seethes with quantum fluctuations that create real, measurable forces. Distant objects can be connected by correlations that transcend space and time. The very fabric of reality can be stretched, compressed, and potentially manipulated in ways that challenge our most basic assumptions about what is possible. These discoveries remind us that science is not a collection of absolute truths, but rather an ongoing conversation between human curiosity and cosmic mystery. Each answer we uncover reveals new questions, deeper puzzles, and more profound mysteries waiting to be explored. The speed of light may represent the ultimate speed limit, or it may be just one note in a cosmic symphony whose full melody we have yet to hear. The search for faster-than-light phenomena has led us to contemplate some of the most exotic concepts in all of science. Tachyons that experience time in reverse, wormholes that connect distant regions of space-time, quantum entanglement that creates instantaneous correlations across arbitrary distances. Each of these phenomena, whether real or imaginary, expands our conception of what might be possible in a universe far stranger than we once believed. Even if none of these exotic possibilities prove real, even if the speed of light stands forever as an absolute barrier, our journey has not been in vain. The exploration of cosmic speed limits has driven us to deeper understanding of space, time, energy, and matter. It has revealed the elegant mathematical structures that govern the behavior of everything from subatomic particles to galactic clusters. It has shown us that the universe is both more constrained and more flexible than we might have imagined. The technologies that may emerge from our growing understanding of fundamental physics could transform human civilization in ways we can barely comprehend. Quantum computers that solve problems beyond the reach of classical calculation, fusion reactors that provide clean, abundant energy, spacecraft that travel at significant fractions of light speed, making the stars accessible within human lifetimes. Each of these developments would represent a triumph of human ingenuity and our relentless drive to push beyond apparent limitations. Perhaps most importantly, our exploration of cosmic speed limits has revealed the profound interconnectedness of all physical phenomena. The speed of light is not an isolated constant, but a fundamental aspect of space-time geometry that influences everything from the structure of atoms to the evolution of the universe. Understanding why nothing can travel faster than light requires understanding the deepest principles that govern reality itself. This interconnectedness suggests that breakthroughs in our understanding of cosmic speed limits might come from unexpected directions. Advances in quantum mechanics, discoveries about dark matter and dark energy, insights into the nature of consciousness, or revelations about dimensions beyond our direct experience could all potentially reshape our understanding of what is possible and what is forbidden in our universe. The history of science teaches us that the most revolutionary discoveries often come from investigators who were pursuing entirely different questions. The quantum mechanics that underlies modern technology emerged from studies of blackbody radiation. The general relativity that describes the curvature of space-time arose from attempts to understand the behavior of accelerating reference frames. The breakthrough that finally unlocks faster-than-light travel, if such a breakthrough is possible, may come from research that seems completely unrelated to space travel. As we contemplate the future of human exploration and discovery, we must remember that we are still in the early stages of our scientific journey. Our species has been seriously investigating the fundamental laws of nature for only a few centuries, a blink of an eye in cosmic terms. The civilizations that arise in the far future, with millions or billions of years of accumulated knowledge, may look back on our current understanding of physics with the same gentle amusement that we reserve for ancient theories about the four classical elements or the crystalline spheres that were once thought to carry the planets. The question of whether anything can travel faster than light touches on some of the deepest mysteries in all of science and philosophy. It connects to fundamental questions about the nature of time, the structure of causality, and the relationship between mind and matter. These are questions that may require not just new physics, but entirely new ways of thinking about the relationship between consciousness and cosmos. The search for answers to these profound questions will likely drive scientific progress for generations to come. Each new discovery, each breakthrough in our understanding, brings us closer to comprehending the true nature of the universe we inhabit. Whether that understanding eventually reveals pathways beyond the speed of light, or confirms it as an absolute boundary, the journey itself enriches our appreciation for the elegant complexity of cosmic law. The universe has been patient with our questions, revealing its secrets gradually as our techniques for observation and analysis improve. The cosmic microwave background radiation waited 13.8 billion years for us to develop radio telescopes sensitive enough to detect it. Gravitational waves crossed the universe for billions of years before we built interferometers precise enough to measure their passage. Perhaps the key to faster-than-light travel awaits the development of technologies or concepts that we cannot yet imagine. As you drift off to sleep tonight, let your mind wander through the cosmic vistas we have explored together. Picture photons racing across the universe at their eternal constant speed, carrying information from the distant past. Imagine tachyons, if they exist, experiencing reality in reverse temporal order. Visualize the exotic space-time geometries of wormholes and warp drives, bending the fabric of reality to enable impossible journeys. Consider the quantum realm where particles dance in superposition, and entanglement creates connections that transcend space and time. Think about the possibility that the speed of light itself might be variable, changing with cosmic epochs or local conditions in ways we are only beginning to understand. Contemplate the technologies of the far future that might manipulate space-time itself, creating new possibilities for exploration and discovery. Most of all, remember that you are part of this cosmic story. You are made of atoms forged in the hearts of ancient stars, assembled into patterns of incredible complexity by billions of years of cosmic evolution. Your consciousness, your ability to contemplate these profound questions about the nature of reality, represents one of the universe's greatest achievements. Through your curiosity and wonder, the cosmos becomes aware of itself. The speed of light may indeed represent an absolute boundary, a cosmic speed limit that can never be exceeded. Or it may prove to be just the first of many barriers, waiting to be transcended by future generations of explorers and discoverers. Either way, our journey through these mysteries has revealed that we live in a universe of breathtaking beauty and complexity, where the boundaries between the possible and impossible continue to shift as our understanding grows. Sleep well, fellow traveler, and dream of the infinite mysteries that surround us. Tomorrow brings new questions, new discoveries, and new opportunities to push the boundaries of human knowledge ever outward into the cosmic unknown. The universe awaits, patient and eternal, ready to reveal its next secret to those bold enough to ask the right questions and persistent enough to seek the answers. In this grand cosmic dance of matter and energy, space and time, we are both observers and participants, questioners, and part of the answer. The speed of light barrier stands before us, formidable and mysterious, challenging us to understand not just its nature, but our own place in the vast tapestry of existence. And in that challenge, in that eternal human drive to explore and understand, we find perhaps the most profound mystery of all, the emergence of consciousness in a universe that seems, through us, to be coming to know itself.